Hello, knowledge seekers. Welcome to Remedial Tutorials. This is mathematical induction. This is not necessarily a proof method. This is a tool required in a lot of proofs. And it's very important. It's used in computer sciences. It's used in math. It's used pretty much everywhere to prove that something holds forever. And that's the most important part, is for something to hold forever. So what is induction? Well, induction has three main steps. It has a base case, which is basically that this first thing is true, and I will compare this to going up a ladder. So suppose you have the beginning of a ladder, and you want to make sure that there is a first step on the ladder. So this first step going up is the base case. Now, the interesting thing about the inductive hypothesis, which is the second part, is that you assume something is true for any number less than or equal to some number k. So what we're doing here is we're going somewhere up the ladder, and we're picking some arbitrary step, and this is k. And then you want to show that k plus 1 is true. So sort of what this is saying is that, okay, if I'm at some random step, then I should be able to get to the next one. And that's all it's saying. It's saying, okay, if I pick an arbitrary step, then I should be able to lift my leg, and there should be some next step that I can get to. And if that is true, then you conclude that every n is true, which means that if the first step is true, and from some arbitrary step I can get to the next one, then clearly this is a full functioning ladder, and I will be able to get to the top of my ladder. Now, why is this the case? So you prove that you can get on the ladder. And then you prove, hey, well, since I got on the ladder, if I go to any random step, then I can go to the next one. Why does this show that, okay, I can go from this first step to the second step? Well, if you're not sure, then we say, okay, well, we'll just say that our k was this first step. Okay, well, then I can get to the next step. That's fine. Okay, now that I'm on the second step, let's make the second step be k. And we know that k plus 1 is true, so we can get to the next step. And this will just keep going on and on and on forever, and eventually you're going to get to the very top of your ladder. So that is the ladder analogy for induction. And if you want to see a logic example, check out the Natural Deductive Logic series on my channel. It is actually just a video called Mathematical Induction. I literally go over the same example with a ladder, except I do a logic proof instead of what I'm about to show you. And you can get yet another example, since I think a lot of the courses I'll be doing will require at least one video of mathematical induction, a propositional logic example after this first one. Okay, so let's show that 1 plus 2 plus ... all the way up to n is equal to n times n plus 1 over 2. Well, we need to start with a base case, and we need to assume that n is equal to 1. Now we have to prove that this holds for the first number. So what we're saying here is that 1 is equal to 1 times 1 plus 1 over 2, which is equal to, of course, 1 times 2 over 2, which is just equal to 1. So this is good. Now, the inductive hypothesis is where people get a little bit tripped up the first time. So what I do is I say, assume n less than or equal to k is true. So what this means is that 1 plus 2 plus all the way up to k is equal to k times k plus 1 over 2. Okay, so now I have to show that k plus 1 is true. So what does this involve? Now, essentially, we're going to go one step further. So we say that 1 plus 2 plus all the way up to plus k plus 1 is going to equal k plus 1 times k plus 2 over 2. All I did here was I put in k plus 1 for k. That's all I did. Okay, so where do you go from here? Well, the assumption is the most important part of a good inductive hypothesis, since what we have here is that this part right here, this 1 plus 2 plus all the way up to k, is equal to k times k plus 1 plus 2. This is part of our assumption. So what we can do is we can plug this in. So we have k times k plus 1 plus 2. We can just add k plus 1. And now we just need to show that this equals k plus 1 times k plus 2 divided by 2. So we can do some nice algebra here, and we will get that k times k plus 1 times k plus 1 over 2. This equals to k plus 1 times k plus 2 over 2. Again, I just found a common factor and put it all together. In fact, this would be plus k plus 1. So on the left here, we have k squared plus k plus 1 over 2 is equal to Well, let's factor this out. K squared plus 3k plus 2 over 2. And when I take a look at this, I see that my math is just a little bit wrong. This should be plus 2 times k plus 1. When I fix my mistake, which means this will be k squared plus k plus 2k plus 2. And we can see here that if we collect like terms on the left side, they will actually equal to each other, which means that we have shown that k implies k plus 1 to be true, which means that we have shown inductively that this statement is true. And I know this might seem a little bit confusing to people, like, wait a second, why does this work? Like, we've assumed that this is true right here, but then we just use it in our proof, and it doesn't seem weird. It seems like we're making a circular argument. And that is one of the first things that you'll say when you first see the proof is, isn't this a circular argument? But again, it's just logic. If we say, whoops, that is another proof there. If we say that by
arrow psi is true, then if we assume phi, we should get to psi. And it's a hypothetical thing. We've hypothetically assumed the first part is true. Therefore, is the next part true? And if that is the case, well, everything was arbitrary, so the whole thing is true. So hopefully you followed that. If not, you can always leave comments. But what I'm going to do is I'm going to do my favorite exam question ever. I love this exam question. I think it's great. Show that the complement of A1 union A2 all the way up to AN is equal to the complement of A1 intersect the complement of A2 intersect all the way up to the complement of A sub n. So this is a set theory proof. And the reason I like this is because a lot of people don't see it coming and they're a little bit confused on what to do because it's induction, which is weird. Okay, so for the base case, what's interesting here is saying n equals 1 is true is a little bit weird, but what we have to do is we have to show that A1 union A2 is equal to the complement of A1 intersect the complement of A2, which we know just by De Morgan's that this is true. So the base case is handled. The inductive step is a little bit more interesting for this because we assume that A1 union all the way up to A sub k, the complement of that is equal to this whole thing right here, which seems like, well, I just proved the result, but that's not really the case. And you're saying, well, wait, why do I even have to do this? This proof is ridiculous. And I will admit, it's a tiny bit ridiculous, but follow along here. So we just assumed that this first part is true. Now we have to show that it's true if we add one more in. So what we do is we say, okay, let's do what we did before and get this whole complement, but let's bracket the first part, and then we'll put in this union for AK plus 1. Okay, well, let's just do De Morgan's here, just like we did in the first part. Okay, so with De Morgan's, we have this whole first part where it's not going to do anything with the union yet because we can't do it yet. But then the second part becomes, okay, an intersection with AK plus 1 and the complement of that. So that's fine, and that's by De Morgan's. But we know with our assumption here that this other section is going to hold as well. Therefore, this complement of A1 union all the way up to A sub k is actually just going to be the complement of A1, intersect all the way up to A sub k, intersect, and because of the previous step we did, we know that this is also going to intersect with A sub k plus 1. And this is by our assumption, so we have thus proven that this holds. So really, while this is... you're saying, well, why do we have to do this? This seems a little bit unnecessary. You just have to show that the next step holds. So if you add one more in, then you can still do it and you still get the same result. Of course, we know that when we always have the same operator, the brackets don't matter. So you can see that this conclusion actually turns out to be our original assumption. So everything was okay there. If you have any questions on induction, leave them in the comments below. You have a proof that you're not sure where to start with, and it is for a discrete math 1 course and involves induction, then please leave it there. I would love to at least start you off in a good direction or give you a link to something that might help.